In this video, we are going to be talking about chemical equilibrium and how to use an ICE table. So in this question, we have a 1 liter container filled with 0.1 moles of A2, 0.15 moles of B, and when the system has reached equilibrium, 0.08 moles of AB have been produced. So what is the equilibrium constant, K, for the reaction? And the reaction is A2 plus 2B in equilibrium with 2AB. So this is the equation for calculating K. We take the product concentrations and put them in the numerator. We take the reactant concentrations and put them in the denominator. And the exponents are the coefficients from the equation. So because AB has a 2 coefficient, it gets squared. And because B has a 2 coefficient, it also gets squared. Now, the important thing is that these concentrations must be at equilibrium. So I can't just plug in my initial conditions that we're told we start with at the start of the reaction. We have to figure out how much is present at equilibrium. So an ICE table is something that we build that lets us look at the initial conditions, the change in conditions, and the equilibrium conditions. So that's where the ICE comes from, ICE, initial, change, and equilibrium. So we're going to look at our initial conditions first. Initially, we have 0.1 moles of A2 in a 1 liter container. So because the K equation has concentrations, I am going to use concentration in my ICE table instead of using moles. So I have 0.1 moles per 1 liter of A2. I have 0.15 moles per 1 liter of B, and AB is not really mentioned at the initial conditions. All we know about AB is that at equilibrium, we have 0.08 moles. But in our starting conditions, they don't tell us anything, so we can say that at the start of the reaction, we have 0 molar of AB. So these are our initial concentrations once I plug in those values into the concentration formula. Now, I mentioned that we know that at equilibrium, we have 0.08 moles of AB. So that is equal to 0.08 molar because we are in a 1 liter container. Now, what's going to happen as we proceed towards equilibrium is that we have to react our reactants and produce our products in order to reach a balance between products and reactants, giving us our equilibrium constant. So we have to lose some of our A2. We don't know exactly how much A2 is being lost yet, so I'm just going to refer to this as minus X. The negative just implies that we are losing A2. The X is how we describe that it's an unknown quantity. And because of our 1:2 ratio of the A2 to the 2B, every time we lose one equivalent of A2, we're going to lose 2 equivalents of the B. So the coefficient to your X term should be the same as the coefficient from the chemical equation. So because it's a 2, it's going to be minus 2x. The AB is going to be getting produced. So instead of having a minus, we're going to say plus 2x. The plus implies that we are producing the AB, and the 2 comes from the fact that every time we react one A2, we will produce 2 ABs. So if we lose X amount, we are going to gain 2X amount. So at equilibrium, we add the first 2 rows together. So if we add together the 0.1 molar of A2 with the minus X, we get 0.1 molar minus X. For B, we have 0.15 molar minus 2X. And for AB, well, what we've kind of learned is that 0 molar plus 2x is equal to 0.08 molar. So that means that x has to be equal to 0.04 molar. If we've gained 2x and gotten 0.08, each x has to be worth 0.04 molar. So let's apply that to our equilibrium row for A2 and B. If we, instead of writing X, write 0.04 molar, then we can figure out what our concentrations will be at equilibrium for both A2 and B. So for A, we end up with 0.060 molar once we subtract our 0.04 from the 0.1. And for B, when we take 0.15 minus 2 times 0.04, we end up with 0.07 molar. So we're trying to solve for K. So we need to take our equilibrium concentrations and plug them into our K equation. So let's go ahead and do that. K is equal to 0.08 molar squared over 0.06 molar and 0.07 molar squared. So plugging this all in, we can figure out that K is equal to 21.8. Now, I do want to just note that K has no units. So even though we have units of molar in our equation for K, even if there are units left over after doing our calculation, K should not have any units. This is just our convention that we use as chemists when we are talking about equilibrium. So tune into our next video. We're going to do another example where we use an ice table, except in that version, we are going to be using our K value to solve for X.